Mars, man's next giant leap. Today, SpaceX was going to launch astronauts to the International Space Station, the first time that astronauts have launched from Kennedy in a very long time, since 2011 or so. It was scrubbed. Hopefully, in the next few days, we'll see some astronauts launch from the Kennedy Space Center again soon. Why are we looking at Mars right now? What's the reason? What's the point? When we look at Mars here, we notice that there are massive canyons. There are these pockmarks, which are actually massive volcanoes. The largest volcano in the solar system is Olympus Mons on Mars. There's evidence here that it was once a dynamic, vibrant place. At some point, plate tectonics must have occurred here on Mars. What we found out recently with the Mars InSight, not rover, but lander, we've noticed that there are Mars quakes, but they're nothing like Earth's. Mars is not dynamic. It's not volcanically active. It's pretty much a dead planet. But Earth is a lot different. Let's fly over to it. Phew! We're going to go warp speed right now. From Mars to Earth. And we're going to see a whole different place. That's for sure. A place that's familiar to you and I. And also really familiar to the astronauts that are about to go up into the International Space Station. Okay? And here we are. All right, we've arrived. As you can see here, guys, this is the terminus between daylight and darkness. Let's move our perspective here just a little bit. All right, so we go into the light. The sun is behind our view, and it's casting its light directly onto the Earth, but it's reflecting its light back towards us. If I focus in a little bit, where are we, guys? Can you guess? Just by looking at the landmasses. The Indian Ocean's down here. Here's the subcontinent of India, China over here, Australia where the kangaroos are down there. Soon, those two astronauts, I think Benkins is one of them, I'm forgetting the other astronaut's name, will be going up. And this is what their perspective will look like. We're actually way too far away from the Earth, though, than they're going to be. They're only going to be about 250 miles above our surface. That sounds really high up, but their perspective is going to be more like this, probably. Gets a little bit blurry there. Okay? Now, why do I bring this up to you? Has the Earth itself always appeared this way? Well, us human beings, maybe evolved over the last 200,000 years or so. We've never known anything different. It's always looked like this to us. But what about millions of years ago? What about 65 million years ago? Or 150 million years ago? Did the Earth look different than it does today? And the answer is absolutely. It's changed a lot. The topic of this screencast that we're having today, guys, is this. The theory of plate tectonics. We're going to spend some time together just going through about maybe 9 slides or so. And then we're going to discuss the assignment for this week, which is going to be 4 questions that will ask you to use your Earth Science reference tables, the textbook chapter I provide, and also the screencast that we're going through right now. So people have been wondering about the dynamic Earth for a really, really long time. And make no mistake, guys, when people first looked at the maps of the world, all right, what's the number one thing that jumps out at you? Well, most people would say that, some of those continents kind of fit together, almost like puzzle pieces, right? And that's true. All right, they do. Specifically, South America and Africa fit together really, really well. Madagascar kind of clicking in to Africa, and I think even elementary school students can really see that. Okay, but there was one scientist that really brought it to the forefront. Okay, and his name was Alfred Wegener. Wegener, what he did is he came up with his theory of continental drift. And really what that stated was that there was once this really large supercontinent called Pangaea that he coined. It means like entire Earth, the whole Earth. That all the continents were once one. And then over millions of years, okay, the continents themselves started to slowly drift apart. Okay, he was onto something. There's no doubt. The mechanism is not really true, and it's been discarded, over the last probably 50 years or so. But he was truly on to something here. Okay, so about 225 million years ago, Pangea existed, and that part of it's definitely true. Okay, and really, as the dinosaurs started to evolve from the Triassic to the Jurassic to the Cretaceous, that Pangea started to break up into what we currently see today, which is the present day Earth that we currently reside. Okay, so right around the Permian extinction, that's when Pangea started to break apart. Okay, awesome. Now, it took until probably post World War II, after the 1940s, into the 1950s, into the 1960s, where multiple geologists from all around the world put their efforts together and came up with the theory of plate tectonics. Now, when you think about theories, right, these are the things we hold most dear, right? For example, the theory of evolution. Really, you can't learn biology, molecular biology, genetics, ecology without understanding evolution. You also can't learn geology without understanding the theory of plate tectonics. What does it actually state? The theory of plate tectonics states that the Earth's crust is broken up into plates. Think of it like you have an apple, and you have that kind of fleshy interior of that apple, and then you have like that I guess the crust would be the skin of the apple. Think of it that way. And the Earth itself is broken up into different pieces, or that skin is broken up into different pieces. There's actually over 20 of those pieces that are floating on like this plastic asthenosphere just beneath the crust. Now, what the theory of plate tectonics states is that the movement of those plates causes the features or creates the features and causes the events like earthquakes and volcanic eruptions that happen on Earth's surface today. What you see here, guys, are all the different main plates around the world. We live right around here. Okay, let me take out my pen, do some drawing here for a second. Okay, why not, right? Maybe we'll do, I don't know, what color should we use here, guys, today? Let's do a red. Okay, all right. We live, as you know, in North America. Okay, so we are right around here. That's us. Okay, we're not really experiencing too much volcanism, none actually. We're not really experiencing earthquakes. And can you imagine why? Well, when we look at the closest plate boundaries, they're really far away, right? California, guys, is very far from New York. And Iceland and the Mid-Atlantic Ridge is super far as well. We're talking thousands of kilometers away from us. So there's not a lot of activity happening right here on Long Island. Okay? These are all the plate boundaries that break up the different plates. Now, Alfred Wegener had no idea about this. What he actually thought was that the continents, the land masses, kind of truck through the oceanic floor or the ocean floor, almost like a bulldozer kind of going through a construction site. That really isn't the case at all. It's the Earth's plates that are moving. Okay. Now, how do we know that these boundaries are even there? Let me show you something that I think is pretty impressive. Okay. Alrighty. So let me click out of this. We don't need this anymore. Okay. And we're going to go to our next slide here. And let's play something for you. And let's talk about it anymore. Okay. Let's check it out. Now, as we let this run, guys, for a little while here, right, you're going to start to see the true picture of Earth's plates just kind of come to fruition here. It's really cool to see. I always love seeing this here. And really what we're seeing, guys, is we're seeing a map of earthquake epicenters that's kind of in real time through from 2000, now we're up to 2004. And do you guys notice something, guys, as you see all these earthquakes happening on Earth? Is there a pattern? Can you see it? Okay. Well, stop the film here. Hopefully, you're going to start to see something that jumps out at you, and that's a pattern or patterns that come into view. Okay, so let's take a look at what the patterns are. Okay, so I'm going to use kind of my drawing option here and try my best to draw the best I possibly can here. All right, and let's try to fill this in and maybe draw in some boundaries here or some interfaces between plates. All right, that kind of jumps out at us, right? So I'm going to go to the Atlantic Ocean, which is right over here, and slowly draw in the pattern of earthquakes kind of going right down this way. Okay, you guess what this is, guys? We call it the Mid-Atlantic Ridge, right? Then we can draw in some more patterns. Let's go around the Pacific this way, near Alaska, through Canada, past California, Mexico, all the way down the spine of South America, right? Then you can go the other way, down this way, right? All the way across the Pacific Ocean, like that, okay? You can even circle around in the Pacific this way. So, what am I doing? Like, what are we actually seeing here? You can even see this kind of boundary here, just north of South America. And what are we doing? What we're doing, guys, is we're discovering Earth's lithospheric plates, right? So what I can do now is label a few of them with you. And you can take out your reference tables, go to page 5 of your reference tables to kind of follow along while you're actually watching this, right? So what would this be over here, right? Well, clearly this is the Pacific Ocean, right? This is the Pacific. And then over here, right, will be the North American plate. Down here is something unique that you might not have ever heard before, is actually the Nazca plate, like so. Don't worry, I can type, right? I can't type really well. And then you'll see, guys, they all just kind of come to fruition just by looking at the pattern of earthquakes only over the span of 4 different years. And again, this is something that Wegener never knew. So what I'm going to do, guys, is now get rid of all this stuff here and go back to the PowerPoint. And I want to talk to you about the main types of plate boundaries that are there. And really, that's it content-wise. And then we'll talk about some questions that you're going to have to do. Okay? So let's do that. Erase that. Get rid of this, guys. Let me escape out of the screen. Okay? And we're going to go back to our PowerPoint here. Okay, so what are the 3 main types of plate boundaries that you can come across? This is actually a photograph of this really awesome model in the California Academy of Sciences in San Francisco, and it shows, that 3D image of the Earth and Earth's lithospheric plates. Okay, so the first type, guys, is convergence. So a convergent plate boundary is when you have 2 different plates, and they're on this collision course. Okay. So sometimes, guys, you'll have, an oceanic plate and a continental plate. And then as they're moving together, the oceanic plate over here is more dense, actually, and it's going to dip beneath the continental plate. So it's going to look like this. So they're coming together. Oceanic plate is more dense, and it's going to dip beneath the continental plate. Okay, we call that subduction. Sometimes you can get continental colliding with continental, which kind of crunches together to make really young mountains and tall mountains. You can also get oceanic crust and oceanic crust coming together and also colliding too. Depending on the age of the crust, the older crust will be a little bit more dense and will dip beneath once again, and you'll get subduction too. There's also, guys, divergent plate boundaries. So if you know your vocabulary, right, guys, divergent means moving away, right? Moving away. This is what's happening in Iceland. This is what's happening at the East African Rift Valley. The actual Earth is pulling apart, and this is what drives the mechanism of plate tectonics, all right, at divergent plate boundaries. And the last one, guys, are transform plate boundaries. And this is like San Andreas. It's kind of like when 2 plates kind of slide past one another, All right, like that. Okay. So to review, guys, we have convergence, boom, divergence, bang, transform, slide. One of my favorite handshakes in all of our science. All right, guys. So let's take a look at questions for the week, guys. It's embedded right here in the screencast, ladies and gents. These are your questions for the week, and I will post them. And pretty much, guys, there are four main questions. Question one, guys, is what evidence did Alfred Wegener have to support his theory of continental drift? So it's something I didn't explain. You're going to have to look it up. Identify and explain three pieces of evidence that supported his claim. Two, using page 5 of your reference tables to help you, state the likelihood that an earthquake or volcanic eruption may occur on Long Island. That is something that I did talk about in the screencast. You might want to rewind. 3, using page 5 of your reference tables, classify the following boundaries as either convergent, divergent, or transform, A through D. And lastly, 4, convergent and divergent plate boundaries both have significant features that are associated with them. Now, those features, guys, are mountain ranges, rift valleys. What else can we say? Multiple young mountains, oceanic trenches, all these different features that are associated with them. You're going to create two charts that identify and explain the main features of both convergence and divergence. On the next page here, I give you an example of what that actually looks like. Let me go back. Okay, here's an example of that. Here's a convergent plate boundary chart, guys, provide at least 3 features. If you notice here, what I've done, guys, is I've written down young mountains. That's a feature of a convergent plate boundary. And then I've given you a description and an example of that. I'd like you to do at least 3 for convergent and 3 for divergent. All right, guys, this is Mr. Cloud coming from my home in North Belmont, New York. I hope everyone's doing really well, and I hope to see you soon, guys. Take care.